Hello, everyone. My name is Vytautas Valancius, and today I'm going to talk about money. So before I start, I want to credit my collaborators, Christian Lumezano, Nick Feamster, Ramesh Jahari, and Vijay Vazirani. Most of us are from Georgia Tech, but Ramesh Jahari is from Stanford University. And I especially want to thank Todd, who warmed you up for some math, because in my slides I will have some math, hopefully not too much. So let's get started. So what's the transit pricing? How is the transit price today in wholesale transit, internet transit? So in the conventional setting, let's say you have a provider, big guy like Cogent, and you have a customer like Georgia Tech. So we're not talking about home users. And what's happened in most cases, not in all, but in most cases, that you have a so-called blended rate. So you have a single price in dollars for megabits per second in a month, usually measured with 95th percentile, as was discussed yesterday. So the interesting thing is that it's charged each month on aggregate throughput. And by aggregate, what I mean by aggregate is that we have some flows from Georgia Tech that perhaps are going to European Union, and they're definitely more costly than to deliver flows who are just going maybe locally across the street. And this sort of blended rate price is set to recover the total cost plus some margin for ISP to survive somehow. So it is convenient for ISPs and clients, but the thing is that it can be inefficient. So let me sort of talk, where is that inefficiency coming from? So what we have is we have uniform price yet diverse resource costs. So if you look at the client has no incentives to converge to conserve resources to costly destinations. So Georgia Tech, since the price is the same in the end of the month, they will not think twice, whether they want to send, to European Union or not. And if you look at the ISP side, actually, there's no incentive. There's lack of incentives to invest into resources to costly destinations. So instead of signaling back the resource cost through price, ISPs signal the cost through congestion. So in economics, it's a well-known concept, and it can result in Pareto inefficient resource allocation. So that can cause potential loss to ISP profit, and it can cause loss in consumer surplus. So you can think of consumer surplus as sort of consumer profit, or the value that's left to consumer after they pay their monthly bill. So the alternative to this blended rate pricing, where you have one size fits all, just one price, and then you send whenever you want, is tiered pricing. So what is this tiered pricing? So essentially, you could price flows based on cost and demand. So one flow class could to Europe could cost more, and the flow class to US might cost less. So the interesting thing that actually some ISPs in this room already use such tiered pricing, and not for all customers, perhaps to more sophisticated customers. And examples of such tiered pricing is, let's say, paid peering, or charging less for on-net traffic. We have this thing not very often talked about, but there is also so-called backplane peering, where you provide a discount for traffic if that traffic can be handed off to peers in that same local exchange where the client is located. And you also have forms of regional pricing. So let me just go more through an example how this regional pricing would work. So you have, let's say, again, Cogent with Georgia Tech. You have, again, these flows. One flow is more costly than another, and then Cogent essentially prices these flows accordingly. So there are different ways to implement that. Some people choose to use perhaps two different VLANs and different SMP counters to account for these flows, and in the end they present maybe one bill with two lines. That was your more expensive traffic, that was your less expensive traffic, this is how much you have to pay. Now, the interesting thing that in the internet, all the cases that I know and that we discovered through talking with many providers, that it's very limited in use. So we saw at most, perhaps, in very extreme case, we saw 6 pricing tiers between a provider and a client, and it was a very sophisticated scenario. So it's a very interesting question. Why in the internet we have pricing with so few tiers. And it's an interesting question because if you look at the other networks, other transport networks, such as parcel delivery or airplanes or trains, actually, if you think in terms of pricing tiers, they have many, many more pricing tiers. So even discounting things like quality of service, how fast you deliver packets, just in terms of how much does it cost you deliver this best effort packet, we end up pricing very often with very few tiers. So the question, we are researchers from university, for economists, for econometricians, it's very interesting why is that so? And the question is, how efficient is such tier pricing? Are we close to optimal or are we far from it? And in the other words, can ISPs benefit if they would have many more pricing tiers? So the very, very extreme case would be that you have a client and you're a provider and you're pricing every single destination in the world at a different rate. And that's very extreme. So the question is, where can this extreme go? So to answer this question, how efficient we are and how many tiers we would need to have, it's very hard. Essentially what we need to do, we have to have some way to test the effects of this tier pricing to ISP profit. And it's a very challenging task. So the approach we take, we should be able to construct an ISP profit model that accounts for demand to different destinations or different flows. And that same model should account for the servicing cost of these flows. So for each flow, you have to have a model, how much revenue it can bring and how much demand you'll have on that flow when you change the price. And what's the end cost for servicing that flow. The other important thing that, we can't just create a model in the air. We have to drive it with some real data. In our case, actually, we do drive it with real topology data from ISPs and with real traffic data, traffic matrices from ISPs. So the question is sort of how to design these models. And then the last step is when we have this parameterized model, actually then we can play different pricing games with the model and see, what if ISP, with these given consumer demands and these given servicing costs, what's the most optimal setting for ISP to price their traffic? So these first two steps is what excites econometricians. And the last step is essentially number crunching, which is the most important for this audience, I think. But I still will go maybe next 5 slides through first and second step to convince that we did our best to come up with as robust model as we can to capture a lot of possible scenarios of ISP networks. So at the very, very high level, what we say, and it's almost impossible to argue about it, is that profit is revenue minus costs, right? And each flow can have some revenue, maybe it's even negative revenue, and each flow perhaps have some cost, maybe some of them even zero. But essentially, if you sum up through each flow, that should be your profit. Now, the way we look at flow revenue, it's essentially price that you price, this 95th percentile, multiplied by the traffic demand. And by traffic demand, I say that it's essentially some function of price. So when you will price if you decide to offer instead of one pricing tier, if you say that now we're pricing local traffic cheaper and global traffic more expensive, perhaps over some time the demands will change. Maybe some customers will migrate to your competition, or maybe you'll get some customers from your competitors, or maybe the customers will just adjust their own inherent demand. So essentially, traffic demand is some function of price. And the question is, how do we model and discover these demand functions? That's where econometrics kick in. Now, the next question is, servicing cost, and that's a very, very hard question. How do you model if you deliver traffic from Georgia Tech to Philadelphia, how much that flow costs your network? It's very hard to answer, and there are many ways to look at it. And essentially, what I'll go quickly through the slide is I'll sort of go through the methods of how we model that part. So at the very high level, the whole modeling approach takes 3 big steps. So actually, we have these three green boxes at the top is actually what we have from service providers, from the ones we have contact with. So we have current traffic demands. We know how much customers are sending, let's say, from Georgia Tech to Philadelphia. we know current prices. We know how much this traffic is currently priced. And we know network topologies of these service providers. Now, the first step, we will discover a sort of family of demand functions that might represent the consumers of the ISP. So we'll take the traffic demands, the currently observed traffic demands. We know the current prices, and by applying a couple different demand models, we'll come up with a family of functions that can represent these consumers. Now, the second step is actually the cost. And from network topologies, if we apply some cost models that I'll go through in more detail, what sort of cost models I'm talking about, we can find relative costs. So given the topology, and having, let's say, assumption that the cost is, let's say, some sort of distance, and I'll have a caveat later that's not always the case, but let's assume for now that, let's say, cost is some function of distance. Given the topology, perhaps I can say that, this traffic, it costs you 2 times more than the other traffic, but I don't know the dollar value. Is it $100 to $200, or it's millions of dollars, right? So what we do, it all plays out in the end very nicely, is essentially having these demand functions and having the current prices and having these relative costs. There is a very neat trick of how actually we can resolve the absolute costs. So let me go through all these 3 steps very quickly. So how do we find demand functions? How do you find sort of it's also called price response functions that represents your customers? So you want to price. If you set the price higher, perhaps eventually the traffic will fall down. If you price less, perhaps you'll attract some traffic from competitors or inherently. So in econometrics, the canonical commodity demand function is essentially some function of price, valuation, elasticity, where valuation is how valuable the flow is, and elasticity is how fast demand changes with price. So for example, this is very simplistic, the 2 demand functions. One represents inelastic demand, so when we change price, the demand doesn't change much, and the other is more elastic demand, which is when we change price, the demand changes a lot. So this elasticity parameter is very useful in the model because when you vary it, you can model different types of consumers or different types of POPs. Maybe in one POP you have a lot of competition, and you can think of as a higher elasticity. When you change the price, more users will switch in this competitive environment. If you have a POP that's not very competitive, perhaps there is less elastic demand because less of customers will switch to alternatives. So the question is, how do we find these all parameters? I'm talking so far very in abstract way, but what are these parameters? How do we find this function? How do we find valuation and elasticity? So if we express this canonical demand function inverse, and if we express valuation, if we try to find valuation, the interesting thing to observe is that actually we know the current prices, we know the current flow, we know the current traffic matrices. The only thing that we don't know for these possible demand models is this elasticity. So what we do in our simulations in the very end, the results that I'll show you later, we just swipe through the huge range of elasticities and see whether it changes the results in any significant way. So this sort of helps us to find these valuation coefficients, and the only thing that we assume when we claim upfront that we don't know actually is the exact elasticity of your customers. So by this point, we managed to find some functions that represent, when you change the price, how much your traffic will increase or decrease. So the next step is how do you model cost? And this is very, very hard question. And it's a very hard question because I think if I ask anyone or every one of you, how would you think about cost of your network, everyone will have different answer. And because of that, actually, we didn't choose one model. We said, there might be so many different ways to model the cost. Let's do it in many ways. So we took linear cost model, we took concave cost model, region, and destination type. I don't know why they have this arrow here, but essentially the x-axis is distance, and the y-axis is the cost that we assume in that model. So you see the first 3 models model cost, that sort of would correlate with the distance that you have to deliver your traffic to. So again, the first example that perhaps for Cogent it's much more costly to deliver traffic to Europe than across the street in Atlanta Exchange, right? So the last is sort of modeling the last model, destination type. We just sort of assume that perhaps maybe delivering traffic to customers is cheaper than to delivering traffic to peers because the customers pay you back something. So let's just focus for a moment on this linear cost model. What could you do with this model and how it's flexible? So as you see, this linear relationship doesn't start at 0. We have some sort of base price. So if that would start at 0, we would assume that, let's say, with 0 distance, you have 0 cost of delivering traffic. And perhaps it's not always the case. So in our model, we can plug different parameters as assumption of what would be the base case in some hypothetical network. So if, for example, if you believe that all your costs are marginal, it's only just hooking up the client, the only cost, and delivering traffic over different distances, there is no difference, then you can just assume that your base cost is very high, and then there's just a flat line. So we played with all these different models. So the thing is that what these different models give us, we can look at the topology, right? We see the distance, how much these flows are traveling in the topology. And in some of the data sets, we actually see, whether it went to clients or peers. And from that, you can sort of infer relative servicing costs. So again, you can perhaps say that this is 2 times more expensive than another flow, but you cannot, at this point, you cannot yet say, is it $2 versus $1 or 20 versus $10, right? So essentially, in our model, these real costs is essentially the relative cost scaled by some parameter gamma, which we don't know. And that will lead to only one slide that has some math in it. And essentially, how do we normalize this, this cost and demand? So if you look at profit where we started, it's essentially some function of the prices that ISP is setting. And then because of valuations and elasticities, it results in some demands, and on the cost of servicing the flows. So let me just go very quickly through it, but if you just take first order condition of your profit function in terms of price, what you see in this formula is that actually the price, we know the valuations and elasticities in this first step. What we don't know is the real costs. And when I say real cost, actually, we don't know this gamma parameter. The relative cost we can get from our models that we assumed in the slide before. So from this, if you look at the map, it's not very detailed, but actually you can express this gamma parameter, and essentially it allows you to find this absolute cost, find an absolute cost parameter for each of your flow. How much this flow costs for me to serve. So by this stage, we have sort of data mapping complete, and we've finished these first 2 steps out of 3. And the last step is essentially after we have this model of demand and cost, we can actually play with different pricing models and see can ISP improve their profit. So the last step is essentially number crunching, and the way we do it is a very simple algorithm. We select a hypothetical number of pricing tiers to test. So let's say, what if ISP instead of this one price would decide to charge 2 different price levels or 3 different price levels? Now, when we decide on this number of price levels, we have to map the flows into the different pricing tiers. So there are, if you just decide that you'll price, that you'll have 2 prices, you have to decide: do you put your Asia and Europe into the second pricing tier, or you put Asia into one tier and US and Europe into another tier? So essentially, how do you map your different demands to different pricing levels? So there are different optimal mapping and heuristics that you can find in our paper, what sort of things we tested. But essentially, optimal is very close to the heuristics we came up. And then the last step is you essentially find the profit maximizing price for each of these tiers, and you compute the profit. So we repeat this for 2 different demand models. I didn't really go through them. There's more in my paper. And it's possible to plug in different demand models, if you can envision any. We tested all these 4 different cost models, and perhaps in reality, maybe the real cost, I don't think there is such a thing as a real cost model of ISP, but perhaps the most realistic one would be combination of some of these 4 cost models. We tried these 4 different cost models, and we tried these 3 different network topologies and traffic matrices with the model, and with a huge range of input parameters to see, whether what sort of results do we get. And it's very interesting. It's very interesting because what we got in most of the cases that looks something like this. What we see here is on the x-axis, we see the number of tiers the ISP choose to price. So you can immediately notice that it's 1, 2, 3, it goes to 6. And we're thinking initially perhaps we'll have to plot these graphs with hundreds of tiers. And on the y-axis, what you see here, the unit 1 is the profit that you would get if you would have infinite number of pricing tiers. That is, if you can price each flow at a different price level. So what it tells us that, let's say at 6, if you utilize 6 pricing tiers, it's your benefit that you get is almost identical as if you were charging every flow differently, right? And you essentially are getting about a little bit less than 80% of this possible gains that you would get with infinite number of tiers just with 2 tiers. So it was a very interesting observation. So we tried to see, why do we see this? What is happening here? So it is sort of what we see here is in this case we see these 2 tiers, and if you look at the data, it's essentially first tier it would be the very local traffic, and tier 2 would be the rest of the traffic. And we started looking at the traffic matrices. What we noted, and what's actually very different from networks like parcel delivery or airplanes or trains, is that there is a lot of local traffic. So it's sort of this result is sort of testament of how good the caching is, how good the CDNs are of delivering the content. So there is a lot of demand that's very local, and it sort of falls off with the distance. So that sort of causes the shape of this graph. And it's very likely that actually if your network it has maybe very different demand distribution, or maybe very different topology, or maybe different cost model that we didn't try, maybe it would look different. But the thing is that, so the next one slide shows sort of a big picture of, we looked at many more setups, but in this case, in this upper left corner, we see a linear cost model with constant elasticity demand. And then we see the concave cost model with constant elasticity demand, and then we have for the same for different demand model. And what you can see here that all of these graphs they look very, very similar. And again, the sort of the takeaway point is that the demand patterns that we observe in the network and the sort of the cost models that we use sort of drives these results. And it's possible to push the parameters into such extent that you need many more tiers, but it would be the demand would be more heavy towards the long distance, for example. So we didn't find those sort of assumptions very realistic. So for sort of assumptions that we deem realistic, all of the results we saw look like this. So essentially, in conclusion, having more than 2-3 pricing tiers adds only marginal benefit to the ISP. And these results hold for a wide range of scenarios. We tried different demand and cost models. We tried different network topologies and demand matrices. And we sweep through the whole range of input parameters, and the results were annoyingly looking the same. Essentially, current transit pricing strategies are close to optimal. So if you have if you have a couple of pricing tiers with some of your big clients, you're good. If you have only one pricing tier, you might think that this client might migrate to some other provider who might start offering these tiers. So that's sort of takeaway message. And if you have any questions, shoot me email or ask me.
Any questions from the audience? Okay, thank you.